We've looked at how we use integration to find areas. Now we're going to look at some volume questions, but for now we're just going to restrict ourselves to things that have circular cross-sections. And so it's very easy to create a shape with a circular cross-section. All we've got to do is rotate it. So we've got our random function here. If I want to grab this from A to B, and I want to rotate it around, whoop, we get, well, what is it? It's like one of those, yeah, you know, the things that your mother usually likes. They put it out on there and go, don't break it, don't break it, you know, one of those things. Yeah. So how do we find the volume of this? And it's still a very similar idea to what we did with area. With area, we said, oh, look, we've got all these rectangles and we'll add them up. Well, if you think about rotating a rectangle, you get a cylinder. And so basically that's all we're going to do. So rather than go through it all, when we get to extension 2, we'll worry about where it all comes from. But so what ends up happening is we sum up all these cylinders. We know the volume of a cylinder is pi r squared h. Okay, so the h, if you like, is the dx, so the difference in the x value, and there's the pi, and the radius for the picture I've got would be the whatever the y value is. So there's the pi y squared. Pi, of course, is a constant, so I can factorise it out. And so we have pi times the integral from wherever we're going, a to b, of y squared dx, because we're going around the x-axis. That's how you remember it. If we wanted to go around the y-axis, then it would be pi times the integral of x squared dy, because we're going around the y-axis. See? So let's now prove some of these formulas that we know, and just like good students that you are, when you were told these formulas in whatever year it was, you just blindly went, yes, I will memorise this formula and I shall use it. I will trust my teacher. Well, now I know you're a bit older and a little bit more sceptical and you don't trust me. Let's prove it to be true. So if I was to rotate y equals mx, and I'll call that value there h, because if you think about it, when I rotate it, that'll end up being the height of the cone. So it seems a logical thing to call it. We rotate the line round and we end up with a cone. So let's prove that the volume is what we're used to seeing. So pi times the integral of y squared dx, well, y is mx, so let's substitute it in. We get m squared x squared dx. Well, m, the slope of the line's constant, that's not going to change, so I could factorise the m squared out. All I'm really integrating is the x squared. So add 1 to the power over the power, substitute in h, substitute in 0, and there's our formula for the volume of a cone. I'm sure you recognise it. 1/3 pi m squared h cubed. And I saw someone there nodding and go, yes, I recognise it. No, you don't. That's not the formula for the volume of a cone. That's not what you were used to seeing. Because, of course, we don't normally talk about the slope of the cone. So let's get rid of the m. Well, the slope is just rise over run. The run is, of course, the height of the cone. The height would be the radius. So I can substitute in, slope is r on h. Substitute that in. Now you can nod. Ah, yes, we recognise that. That's 1/3 pi r squared h. Okay, what about a sphere? Well, a sphere, we just got to rotate a circle, and we'll get it. Well, in fact, we don't rotate a circle, rather we rotate a semicircle. Rotate it round, and we'll get our sphere. So pi times the integral of y squared dx. Well, it's already got y squared in the equation, so r squared minus x squared is what we'll substitute in. And I'm just going, well, rather than going from minus r to r, I'm using symmetry. And I'm going twice from 0 to r. So I get r squared x minus 1/3 x cubed. Substitute in r, substitute in 0, and voila, 4/3 pi r cubed, which I hope is what we recognise to be the volume of a sphere. So all these different formulae that, well, as I say, you just blindly accepted as true, we can now prove. So let's look at a more interesting shape. We're going to find the volume of it when we rotate a parabola. We're going to rotate a parabola around the y-axis. So let's draw up a picture. There's our parabola. Rotate it around the y-axis and we're going up to 1. So around we go. And we get the shape known as the paraboloid. Paraboloid. Okay. Pi times integral x squared dy, because we're going around the y-axis. So I need everything in terms of y. So x squared, oh, that's nice, isn't it? X squared is y. That's a simple substitution. So y to y. Anyone? Y to y. Because we're going around the y-axis. How many times have we got to do? Jeez. Okay. Integrate. We get a half y squared. Substitute in 1. Substitute in 0. And there we go. We've got pi on 2 units cubed for our volume of that particular paraboloid. Be careful. Make sure you read the question and you know exactly what it is they're asking for. The volume of the solid when this shaded region is rotated about the x-axis. Okay. Now notice I have not just gone the integral of 5x, because it's not the area under the line that I'm rotating around the axis, it's above. So it's like those area questions where it's between two curves. Here we've got two boundaries. We've got the horizontal line y equals 5, and from that we'll subtract our straight line 5x. But of course we're dealing with volume, not area, so we square those values. So the top one squared minus the bottom one squared. And we get 25 minus 25x squared. Integrate that. Substitute in. But of course, if you did it that way, that would be a little bit of a waste of time. Right? Because they're regular shapes that we're going to create. If I was to rotate that, what I would end up with, well, basically a cylinder with a cone drilled out of it. And we have formulas for those. So why worry about integrating? I could say, well, hang on, this is going to be the volume of the cylinder, pi r squared h, minus the volume of the cone, 1/3 pi r squared h, and a lot quicker, we get 50 pi on 3. So remember, the beauty of integration, I guess, is when we have those irregular shapes, things we don't know formulas for. But if we've got a shape where we know the formula, let's not waste time, let's just use the formula. HSC question. So we've got two parabolas there. One's upside down, one the way we're used to seeing it. Find the points of intersection. Well, they'll come in handy. So we would solve them simultaneously, and we end up with plus or minus 2. But they've asked for the actual points. I've only put down 2, 4, but of course to answer this question correctly, I should have put negative 2, 4 as well. Okay. So that shaded bit on the right hand side, we're going to rotate about the y-axis. They've given us a hint. Split it into 2 regions, which of course we have to, because if we're going around the y-axis, again the boundary changes. Because we've got the upside down parabola, we get to the point of intersection, but then it's the right way up parabola. So we need to split it into 2 regions or parts, find the volume. Although it does say or otherwise, which is interesting. Well, there must be another way of doing that. But anyway, volume is pi times the integral of x squared to y. We're going to split it there. So x squared is equal to y. And the other one, I'll make x squared the subject. We get 6 minus a half y. So we've got pi times the integral of 6 minus a half y to y. Y to y, because we, anyway. And pi times the integral of y to y. And I just noticed something. Have you noticed it as well? Look at it very closely. What have I done? It's wrong. Basically, that line is wrong. What? Yeah, that line's wrong. Yeah, say it. What do you think? Yes. Look at the limits. Look at the limits. The 0 to 4 is actually the section with x squared. So I've got the limit. So obviously, whatever answer I'm going to end up with here is going to be wrong. But the idea is right, and that's the important thing. Unfortunately, you can't claim that in the HSC. But no, the idea was right. Okay, so I'll substitute in and get a completely different answer to what it should be. Hey, there's a fun little thing for you to try at home. You can work out what's the actual answer. Wouldn't it be funny if it was the same? Anyway. All right. So 11G.